The speaker is Mingyuan Hu from Northwestern University, and he will speak about skein-valued open Gromov-Witten invariants and cluster mutations. Please.
Yeah. Thanks for the invitation. It's a great honor for me to speak here. And so the title of my talk is skein-valued open Witten invariants and cluster mutations. So before I start, this is a joint work with Schrader and Zaslow. Also, part of this talk is my another paper by them. So let's start. So roughly speaking, the plan is that first I'm going to tell you about some background on open Gromov-Witten invariants, and we will see what's the problem and why we need to use the so-called skein module, and I will build some examples using a method called cluster mutation. Yeah. So let's start. So the geometric setup is we have a Calabi-Yau threefold, or more generally, it could be a symplectic manifold. It's dimension 6, and for example, it could be C3 or the result conical, like the founder of S3. So in this talk, we will be mainly interested in most of the example would be Lagrangians in C3, and L is a Lagrangian. Mathbb 0 just means some condition to guarantee that the molar space is of the right dimension. So the open Gromov-Witten invariance is to count open curves. Here is a very big picture. So we have an L, and L is this Lagrangian serves as some kind of boundary condition. So it's called Lagrangian brane. It's a boundary condition of some, like in string theory called like worldsheet boundary condition. So we're interested in counting such homomorphic curves. It's a Riemann surface with boundary. So the point is that we do not like just count this, because we count the surface with all genus, and it could be have multiple many boundary components. So sorry. So let's say so. So since we know that X is a Calabi-Yau and L has this property called mass log 0. So if we consider the molar space, the virtual dimension of this molar space is of dimension 0. So ideally, we hope to get a number, right? Maybe, at least if we fix the boundary, if we fix the number of boundary components in the genus, fix G and H. So we want to count the number. That's a naive thought. However, there is a problem, which is that this number is not well defined, because if we change the almost complex structure J, it's this number will change. Let's say how this could happen. So if we have a family, of JT, JT is a family from 0, 1 to the like this the modular space of almost the complex structure, and what will happen? So for good J, for good almost complex structure, the modular space of J homomorphic curves is is just some discrete points, because it's of dimension 0 for. So for dense
Sorry, excuse
open,
me. Is it kind of well defined? I understand that the virtual dimension is 0, but is there a virtual fundamental class, something?
yeah, there is a virtual technique here. So there's some virtual, yeah. So I think it's they deal with this in well, Ekholm-Shende, they deal with this virtual problem in their papers. Ekholm told me that he used well, it's kind of subtle, but he used polytope. but I think I talked to some people. People believe that they can also deal with this problem using so-called global coordination structure, but it's not written down yet. In their papers they use polytope. Yeah, you're right. There's some technical issue here about virtual technique. Yeah, but I'm just telling some like vaguely. I'm telling you some story here. So yeah, so all for some good almost complex structure, all J-homophobic curves are good, meaning all curves are like embedded and rigid. So the model space is just a discrete set of points. However, there are some bad points, and when we change this t, this we have to match some. We will like cross this wall. Roughly speaking, the picture looks like this. We start with a J0 and J1, and if we want to connect them at some point, we will meet some bad J. So let's say how this will happen. So let's take the universal modular space, which means it's like you have a family of J and so we have a family of modular space, and we pick up one point in this modular space, which is a J-homomorphic curve, and its boundary of this UT, it lives in L, which is this Lagrangian. It's a three manifold, so it's a one submanifold in a three manifold, and so another way to draw this picture is roughly it's like this. So this is our L, and so it could be something. Sorry, something like this. So there might be some genus here. So when you change this t, there's a family of curves. The topology of the curve looks like this, the boundary. So there's this part of the boundary might go in like downwards, and this part of boundary might going upwards, and at some point they will meet each other. So it's a singular curve which might looks like this. Right. So, and if you just go across this wall, if you keep going, then this part of boundary components goes down, and the other part they will separate again. And so far so good, everything's nice. However, there's another way to resolve this singularity, which is like it looks like this. Its boundary looks like this. So meaning that there's another family of J-homomorphic curve approaching this singular curve, and a boundary looks like this. So if you look at the modular space closely, you will find that on this side there's 2 points, but on this side this just 1 point, because there are this is a singular point in the universal modular space. Yeah, it is a universal modular space. It's not smooth, just a single point. So this side there's 2 family approaching. But if we look at the boundary of these J-homomorphic curves, it looks it just looks like this. So if you have seen the definition of a scheme module, this kind of picture might be familiar. So the solution Ekholm-Shende gives to solve this problem is that first, there are many ways to solve this problem. So like in FOO, they use like they define some A infinity structure here, and using something called bonding constraint. This is just one way to deal with this problem. So I think the subject of open Gromov-Witten invariance is still like developing. So yeah, here. So what Ekholm-Shende tells us that well, in the very beginning, we should not hope to count a number. So instead, we want to remember the information of the boundary of this J-homomorphic curve. So we should remember the information of the boundary as a link inside this three manifold. That's a key idea. So the thing is that we should count this this open Gromov-Witten invariance inside the so-called scheme module. So which I'm going to introduce now. Oh, by the way, is this an hour talk or 15 minutes?
No, it's an hour talk. Yeah, absolutely.
Oh, okay. Yeah, thanks. So any questions so far?
Well, so far everything is clear. In fact, when long ago, I also proposed, without naming the skein module, but to look for the skein relation as a wall crossing. But it wasn't developed. But now I see it's fine. Yeah.
Yeah.
They did it. Okay.
Yeah. I think another important thing is that the virtual technique it's like the symplectic field theory has some development in recent years, so people know how to deal with some technical problems. Yeah, not sure if that's part of the reason. Yeah, so let's just reveal some definition from skein theory. So through this through this talk, we are going to denote R by to be this ring. Actually, this is a field here. So it's we work over a complex field with two formal variables. One is called A, the other is Q, and denote Z to be the thing. For actually we need a oriented manifold. So M is a oriented three manifold. The HOMFLY-PT scheme module is defined to be the free R. First, you take the free R module generated by all the links. So yeah. So an element here is just a linear combination of some links, but we want to model some relations, which is this three. Note that actually we consider framed links, meaning that for each link we pick a section of the polynomial bundle. So it's like you have a link and we fix the port direction of this link. So here for example here on R2 we're taking the blackboard framing, so everything is pointing inward. So I mean in a general three manifold, this which edge is on the top and which one is on the bottom is well defined. Yeah. So to model this three relation, and one example is that for R3 this scheme module is trivial. So meaning that so if we have a link L here, and by this three relation we can resolve all the crossing. So you represent a link L by a link diagram is some lines on R2, and whenever it's crossing you with some crossing, and you can resolve all the crossing by this three, and in the end you get some linear combination of the unknown because there's no crossing, and you can use this relation to replace an unknown by a polynomial. So in the end well you will send L to a polynomial, sorry, PL. This is called the HOMFLY-PT polynomial. And well, notice that there are actually two variables here. So after some change of variable, this will recover John's polynomial. So this is sort of like the most general polynomial, not invariants. Okay. And we will see more examples later. So when for a surface sigma, we use the following notation. We take the scheme module of sigma to be actually it's a scheme module of secant sigma. You can secant the surface a little bit. I is a small interval, and then it's a three manifold. Then so yeah. So it's you can take So you can define the scheme module. And actually, in this case, it is an algebra because you can stack two surface, one on the top, the other on the bottom. So an algebra structure is just this map, right? So and the picture looks like this. You put one link on the top, the other link on the bottom. So that's a product structure. And also a question?
Yeah, I mean, it's about skein module story. Is it known how they behave with respect to the surgery and some functorial things like Kirby moves, whatever?
It's not. It's we know very little about, or we know some examples like torus, but in general, the scheme module is super complicated. But there's one thing in general as for scheme module we know how they behave under connected sum. I think the the scheme module of like M1 connected sum M2 is just the tensor product. And well, we know some examples like I will talk about later. In the torus, it's equivalent to some like double alpha hack algebra. Yeah,
Okay.
that's all. Yeah, in general, the scheme algebra is huge. So yeah. Okay, so for three manifold M, and it's if we this boundary is the surface, so the scheme module of partial M is an algebra, and in fact it has an action on the scheme module of M. It's an action is also this map satisfying some associativity, right? So and it's just you glue the boundary back to M. Oh wait, sorry. This is M here. Yeah. So the picture looks like this. So any question so far? It's basically whatever such an action. And recall that the definition of quantum torus.
I'm not sure how the M does have a boundary. How do you glue the boundary using using the I product with
I is the interval. I is 0, 1. Let's say. So I is
I is the interval, but the boundary is this is I see boundary is a surface. Okay.
Yeah, boundary is surface. And then we glue. So that's
I see. So
that's the definition of
boundary.
map.
Okay. Yeah.
Yeah. Any other question? Yeah. So recall
the only thing is that on the same page your three manifold is the same as the lattice a little bit lower. So you use the same letter for two different things.
Sorry. It's yeah, I was planning to use gamma, but I use gamma later. Maybe let's use N instead. Yeah, sorry. Yeah. So let's recall the definition of quantum torus. So if we have a lattice, well, sorry, let's still call it M, and it has a skew symmetric pairing. Also, so a lattice is just a free abelian group which isomorphic to Z direct sum N to N times. So yeah, and we define the quantum torus to be this thing. Well, if Q is 1, then this is just the function ring of a torus. So it's a algebra free generated by this XM. But for each M in this lattice, we have a variable XM, and they satisfy this relation. And so in fact we have a surjection. So the scheme module somehow it's like all this quantum torus could be viewed as a rank 1 reduction of the scheme module. So we have a surjection. So this surjection is given by adding one more relation. So anyway, the point is that there's a surjection here. So so we already know there's lots of interesting story about quantum torus. So the thing is that the scheme algebra is huge. It's very large, and And morally, yeah, by the way, this is not a rigorous math, definition, but roughly speaking, so the scheme module could be understood as a quantization of the rank infinity local system on sigma. So it's just very vaguely, like morally, this is what you,
Yeah,
because
but let me ask you this GL1 local systems, which is a torus, it's a cluster chart. Yeah, it's sort of elementary cluster variety, so you quantize it.
yes.
What about the skein algebra in general? I mean, is it kind of
Yeah, that's an interesting question. That's the thing that we don't know. Yeah, that's something we want to explore, but I don't have an answer yet. Yeah. But our original motivation to define this skin cluster mutation is to compute open Gromov-Witten invariants, and that's all. But in fact, it should have some relation with the cluster charts on this thing, but that's something we are still working on and don't have a good answer. Sorry. Yeah.
Okay.
So yeah. So. And another example is let's consider the solid torus. So the skin module of solid torus, first it can be decomposed to two parts. One is so this is picture of the annulars of torus. So you should understand that this edge is glued to this edge, so it's an annulars. So and when I draw such a diagram on annulars, it means a link in solid torus. So this part is like everything is going toward like to this direction, and this is everything going toward this direction. So it decomposes to the tensor product of this one, and each of them is isomorphic to the ring of symmetric function. So it's also like it's generated by Schrader. That's the Schrader polynomial. And I can give you some example. This is a picture I copied from paper by Ekholm and Langhi. I don't know how to read his name, but and Nakruma. Yeah, that's in their by their notation. This thing, yeah, actually correspond to our the Schrader polynomial. It lives in the skin positive of solid torus D2, and you should understand that this as like this part and this part are glued together. So such a braid is a link in a solid torus, and that's some examples. That's yeah, there's a partition. When I give you a partition, there's some links, and you'll notice that the number of box corresponds to the number of strands in this braid. So that's a homologic class of this link. So yeah.
Should I think of these as elements of, I don't know, some Fock space or something like that?
Yeah. Well, I think yeah, I actually the thing is that this module is embedded in the can be viewed as a Fock space because this thing acts. The action is that this thing acts on this. So this is just a symmetric function, and I'll introduce this later. So this thing has an action on the ring of symmetric function. So you should view this as not solid torus but real torus. So yeah. Thanks. That's our next example, which is the torus, and the picture looks like this. So you glue the blue edge to blue and red to red. That's a torus. And the skin algebra is generated by this px, and the px is just the geodesic going towards the x direction, for example. So this is p10, and this is p01. Right. So and this is p12 because it's going to the 1-2 direction, and you model the following relation. If you take x to be 1, 0 and y to be 0, 1, you will find this relation is exactly the skin relation. It's easy because if you consider the commutator of x and y, if you want to commute them, and then you will create one more element which is p11, right? So yeah, because yeah, so and note that this is actually enveloping algebra of Lie algebra, and we have a representation given by geometry, right? This representation, actually you can write down this by formula, but this definition but this is constructed by topological geometry. We have
What's Lie algebra? I mean, it's kind of infinite
the Lie algebra.
dimensional, but it's not Heisenberg. It's something.
Yeah, the Lie algebra is just the Lie algebra generated by this px, right?
Yeah, so there is no better description. Yeah. Okay.
There's one thing, because this is isomorphic to the limit n double alpha hack algebra. Some people denote it by this, and the specialization, something like QQ. There's two parameters here when you define double alpha hack algebra, and you take both parameter to be Q, or maybe 1 over Q, so something like that. And there's such equivalence, but I don't know other. Yeah.
Okay.
Maybe there are other way to write this down, but sorry, I don't know. Yeah.
Okay.
And now let's go back to the open Gromov-Witten invariants. Why we need this scheme module? So as I mentioned before, we should count this in the scheme. We should count curves in the scheme module. So here, that's the definition. So we take all curves, like U runs over all open curves, and we should remember, what should we remember the information from your its boundary. So the contribution of a curve is its boundary as a link inside L. So that's the contribution of the open curve U, and they record the information of its genus. Chi is the genus, and this is the linking number of U and L. I mean, it's defined by Ekholm-Shende, because in general U is open. There's no linking number, but that does have a definition. Anyway, so yeah, so that's roughly speaking. So we take we remember the boundary of U as a link inside the scheme module, and then this is like the generating function of the scheme module of open Gromov-Witten invariants. So we call this a wave function of L, and that's it. So the key point is that we must consider all curves, all genus and arbitrary mapping boundary components, because if we go back to this where is it, to this picture, we will find that when we cross this wall, the genus or number of boundary components might change if we cross this wall. So the point is that we have to consider all genus and arbitrary mapping boundary components. And the theorem is that this is independent of J, because if we cross the wall, if you take J.
I'm confused about the U. Are they the curves? Are they not the links or complex curves, or?
So what the U is a curve.
You said the open curves with all genus.
Yeah. U is a curve. Sorry, maybe.
Curve in what sense? It's a real curve or complex curves?
It's a real dimension 2, complex dimension 1.
Okay, so those are kind of a complex curves, because we're talking about the links at the same time.
Yeah. Sorry. It's a complex curve. It's complex curve. It's this map. Also, maybe I'm also like abuse of notation. I'm identifying U sigma and U So sigma is a map, or U is a map, and sigma is the surface. But somehow I'm sorry, I'm abuse of notation. So yeah, U is this map, but sometimes, but yeah, I also use U to denote sigma. Sorry.
Okay, now I get it.
Yeah. So if we have a family of J, we will find that there's a difference exactly lives in the skin relation, so it's well defined inside the skin module. That's the same. Any question so far? Just
Why do you call it a wave function?
well, I don't know this. Actually, this is named by my advisor Eric Zaslow. I think he has some physical consideration, which I
But
don't.
either any, I don't know, differential difference, Q difference probably operator which kills this PCL. Normally, wave function,
Oh yeah, exactly.
equation.
That's the reason because we will see that later it satisfies some equation, and some skin equation. And if we do the rank one reduction, it becomes some like Q differential equation. So
Okay.
actually,
Yeah.
that's how we compute them. We solve those skin relation to compute skin. We solve skin equation to compute this percent L. That's how we compute them. Yeah, thanks. Yeah.
Okay.
And yeah, my remark is that that we know that when L is topologically when it's a solid torus, the wave function lives in the symmetric ring of symmetric functions. So actually, people have computed such a generating function, or they call it some partition function, like a long time ago. By physicists, they use method called like topological vertex, and they get a power series of symmetric functions living here. And if you look at their paper, just some like many pages, just a table, just writing down some key power series, and magically they do. Our computation will show that that they do match up. So now we have this skin. So what?
May I ask? I mean, because yeah, I understand that if your ambient space is compact, then I believe that maybe you can define some virtual fundamental class. I mean, at least in some examples, people did it long ago. But your cotangent bundle is non-compact. So then
that's the thing. So
I'm starting to worry more and more.
But the thing is that it's not compact, but near infinity it's exact. So it's called a Liouville manifold. It's like cylindrical near infinity, and near infinity is exact. And exact thing doesn't bound any homomorphic disk. So this disk doesn't escape to infinity.
Here it's important that your L is conic at infinity.
It's that's important. Yeah.
Okay.
Yeah, thanks for the question. And one example, this another example. I think it's very important, interesting is that if we consider a knot or maybe a link inside S3, and we take X to be the potential bundle of S3, and L is a conormal of K. So this is the 6-dimension symplectic manifold. This is Lagrangian, and the wave function of this L is actually the sum of all color HOMFLY-PT polynomial of K, and this is called large N duality. So this used to be some conjecture, and it's proved by Ekholm-Shende using this skein-valued skein-valued curve counting technique. So somehow this tells us that the HOMFLY-PT polynomial is open Gromov-Witten invariants somehow. Yeah. So because
do I remember correctly that in this example, maybe, no, maybe for unknown. It's quantum dilogarithm or something.
Oh.
This Aganagic-Vafa story.
Yeah.
Okay.
Yeah. But like original large duality is derived from physics, right? This because this side is Chern-Simons and the open Gromov-Witten is like some open string theory, but this is a mathematical proof of like large duality. So and now we are interested in some Lagrangian. Well, we are going to actually compute this wave function. So what we are interested in is a class of Lagrangian in C3, and it's as Ian said, it's cylindrical at infinity. So first, so near infinity, it's a Lagrangian. So let's first construct this Lagrangian. So it's a Lagrangian inside S5. So how do we construct them? So first, we start with a trivalent graph on S2. On S2, and we want to construct a Lagrangian surface inside the first jet bundle of S2. So the idea is to first construct from projection inside S2 times R. So from contact topology, we know that if we have like a singular surface inside S2 times R, and then we can recover we recover a Lagrangian surface inside the first jet bundle S2. So this singular surface looks like this. So generically, it's a 2-to-1 cover. Aside from S2 minus gamma is a 2-to-1 cover, and near a vertex of gamma, it looks like this picture. So this is S2, and this is a projection. So this whole thing lives in S2 times R, and this is our direction. And if we project everything down, it looks like this. And this gamma is indeed the singular locus of this singular surface. And you can imagine that whenever we write down a gamma a trivalent graph on S2, globally we will have a singular surface above S2 living here, and we can take its from projection inside the first jet bundle and then embed it in S5, then we get a Lagrangian surface, and this Lagrangian surface, by our construction, it has a branch cover. It's a 2-to-1 branch cover and branching exactly at the vertex of this gamma. So this let's say so in actually this is a long story, but in short words, it's like whenever you have a gamma, you can construct a Lagrangian surface inside S5. So, and maybe I'll be a little bit vague here. So similarly, by some combinatoric way, you can construct a Lagrangian filling. It's a branch cover over D3, because D3 is a filling of S3. So when restrict to the boundary, it's a Lagrangian we just construct. So long story short, let's first go this. The long story short is that we have a gamma. We call this Lagrangian wave because we have a gamma, and then we can construct a non-compact, but it's cylindrical at infinity. Lagrangian lives in C3, and the picture looks like this. So this is a Horic diagram of C3, and the near boundary at infinity is a genus G surface, and we have a Lagrangian filling. Because L is non-exact, so it might bound some curve. It has open field. So let's look at an example. So this is a tetrahedron graph. Well, it's called here. So it's called tetrahedron because topologically on S2 is this graph is the same as this tetrahedron graph. These are the same. And if you go back to our definition, you will find this the Lagrangian surface we get is actually the so-called Klingfeld torus in S5. It's an exact it's an interesting exact interesting Lagrangian torus in S5, and the Lagrangian filling we get is called Aganagic-Vafa brane. It's started by physicists before, and so, and if you want to formula, this is it. So another way to think about this is that so this is a moment so C3 is a toric manifold. So we have a momentum map, and that's the image under this momentum map, and this Aganagic-Vafa brane will live over this ray. So it's a Lagrangian lives over this ray. So we have, let's say we have C3. This is the momentum map R3, and and this Aganagic-Vafa brane will lives over here. So that's one example. And by in general, we will have like or the boundary infinity might be a high genus curve. So we're going to compute this the wave function of this Lagrangian. So that part might be a little bit fast, but in conclusion, when I will have gamma, we have a Lagrangian, and it looks like this. Any question? Yeah. So if we know that the genus G, the genus of this the surface G, and then L gamma topologically it's it's another type. So it's HG. HG is the solid handle body, right? It's like the filling of this genus G curve, and in the end, the wave function will live in the skein module of this genus G handle body. So yeah, so now the question is that whenever we have a gamma and we want to compute this lives in the skein, or maybe we need to take some kind of completion lives here. Yeah. So and that's a wave function on the generating function of open Gromov-Witten invariance of gamma. Yeah. And so how do we compute? Yeah. So it's so it is important that this L is non-exact actually. So for compact I mean, oh no, wait, sorry. It's important that this L is non-compact and it's cylindrical at infinity, because for compact Lagrange actually, as far as I know, I don't know any tools compute it. But since it's cylindrical at infinity, we have a recurrent relation from symplectic field theory. So because L is like cylindrical at infinity, so near infinity, it looks like the Lagrangian surface times R. Yeah. So yeah, it's like conic, and then so the punchline is that if we come at curves only at infinity, and then times power source, we get the wave function is 0. And why is that? Because
no, I do not understand even what is written. What do you mean? Sum of curves at infinity? I mean, what this product means.
Oh, this product, yeah. Because I will explain this more precisely later. So in the end, we will get something lives equation lives in the skein gamma. So recall that we have an action. We have an action of the skein lambda gamma x on skein of L. So when we count curves at infinity, in the end we will get something that lives here.
Yeah, I'm a bit confused. This your lambda is 2-dimensional or what?
Yeah, lambda is 2-dimensional. But
all
by
right.
this
And
notation,
so when you define it you consider this product with the interval, and
Yes,
you
exactly.
ignore that lambda is a boundary of some Lagrangian. Okay. All right.
Yeah. So, but it's the same because near infinity is this is like lambda times r, right? Because it's cylindrical. So near infinity, this L is a surface times r. So the idea is that if we expand this product, and it would be this would be like we're counting the boundary of some one-dimension moduli space. So it's kind of like in the floor homology, and partial is zero. How you prove partial is zero? Because partial, if you expand all the term, it's like counting some the boundary of some one-dimension moduli space. So a term here actually looks like this. It's like a nodal, a geomorphic curve with a nodal on its boundary, and if you count everything there, you will get a zero. So long story short again. So it's like because this is exact. So when we want to count curves here, we need to fix something called ripcord. We need to, and we can count all curves like going to that ripcord, and for in our case for each surface, that's our that's our gamma, and for each face of gamma there's exactly one ripcord there. So in the end, what we get is that for each surface, sorry, for each face of this gamma, we can count curves at infinity, and we get a relation here. Recall that oh yeah, as I said, sorry, color, let's use black blue. So A gamma F, this lives in the skein module of sigma G. So and psi gamma lives in the skein module of Hg. Sigma G is surface and Hg is handle body, and there's an action. So this dot means an action. So by this trick, this recurrent relation, for each face f of this gamma, we get a equation. So any question for that? Yeah, but I skipped lots of details, but that's a rough idea. So yeah, so the punchline is that you count, well, because L is cylindrical, so you counting at infinity gives you a recurrent relation. So for each face, you get a like skein-valued equation. And so let's say an example. In the case of Aganagic-Vafa brane, as we mentioned before, it's well, the equation we get, it looks like this, where this is unknown, and P0 and P0 is a curve like this, and P11 is the curve going that way. But so as we mentioned before, this could be understood as a quantization, like higher rank quantization of the torus. So it's a quantization of this equation. And if if you're familiar with mirror symmetry, so actually this is a sorry. So this is a mirror curve. This is a pair of pens, right? And that's a mirror curve. Mirror curve of C3. So it's and yeah, and this this equation will if you solve this equation, it will give you the wave function of of this Aganagic-Vafa brane, which we define as so-called skein dilogarithm. So, yeah. Any question?
Maybe yeah. Recall this Aganagic-Vafa. It's like what cotangent bundle to S. Okay, this one.
Yeah.
Now, it's okay, tetrahedron. Yeah, but what it has to do with this Calabi-Yau, which correspond to this curve which you wrote.
That's the story of mirror symmetry. Roughly speaking, it's like people say that for a toric Calabi-Yau and for toric Calabi-Yau, for example, C3, and usually it's an LG model. Here, the superpotential in this case is this one, and it's mirror of this pair of pens. The story come from mirror symmetry, and well, there's some physical reasons. Sorry, I don't really know, but the result is that for example, this is LG model, and the Foucault category of this is equivalent to the coherent shift.
Yeah.
This,
This story, I believe that people in the audience they understand, but what I do not understand, it's a relation of what was written above.
Here.
This skein, whatever story, yeah, how to.
Here. Here it's a recurrent. It's a equation for like, sorry, for this psi Aganagic-Vafa. So this operator will analyze this wave function. So because whenever we have a gamma and we have a bunch of equations for this wave function, and for the Aganagic-Vafa brane, the equation we have is this one. So again, A lives in the skein module of this surface, and psi lives in the skein module of handle body.
So when you excuse me, when you speak about this Aganagic-Vafa, whatever Lagrangian, Lagrangian submanifold, basically your psi counts open Gromov-Witten invariants with some.
Exactly.
Yeah. All right, this I understand, but the quantization of this mirror curve, which is a Q-difference operator, should kill. I mean, maybe I'm wrong, but it should kill the partition function for.
Yeah, it kills the partition function because this operator will kill psi AV.
Yeah, but basically you say that this psi should be understood as a partition function for this mirror dual. Calabi-Yau 3. Okay.
Well, that's some like vague idea because we have three terms here, and somehow we believe this corresponds to this one, and this term corresponds to this one, and this term corresponds to this one. So, but the only mathematically rigorous statement is that this operator analyzes kills psi AV. Yeah.
Can you do it for any spectral curve in C star square?
Sorry, what was it?
I mean, this is a very particular.
Let me see. For quantum curve, it is possible because we can write down equation and then just quantize it. But for skein, we don't know. I see what you mean. Yeah. That's something I would guess, but we don't know how to prove because all example we have worked are only in C3. Yeah, but for other thing, for other curves in system 2, I would guess this might be true, but we just for now we don't know how to do that. Yeah. But there's one thing I know which is like this curve. That's a topic.
Resolve conic folds.
Resolve conic fold. For that example, we have computed. We know how to do that, and this is true. So we write down the equation and we just literally do the quantization and we solve the skein relation, or we solve the skein equation and we get the percent we want. But in general, we don't know.
Interesting. Okay.
Thanks. But anyway, so yes, in conclusion, it's like we have a bunch of skein equation. So this lives in the skein module handle body, and this A lives in skein module of the surface, and we have a bunch of equation, and one for each phase of gamma, and we want to solve. If we can solve this equation, and if we know the solution is unique, then we know we can compute the wave function of L gamma. So is that part clear? Yeah. So how do we do this? We use cluster mutation to solve this equation. So recall the definition of quantum dilogarithm is just written down like this. It's a complicated formula, or maybe not that complicated, but yeah. And then recall what is a cluster mutation. A cluster mutation is just a bidirectional map between torus, and writing down in some formula. And a quantum cluster mutation is just a map between the completion of quantum torus, and it's given by you take the conjugation of quantum dilogarithm. It's like this, and there's a whole story like about this is a whole subject. Yeah, but anyway, so what we need is for today we are going to use this to compute like we're going to define a skein version of this dilogarithm, which looks like this. So let L be a simple closed curve on sigma. So when we write NL, actually it's just a curve like winding around L n times. And if you want a definition, it's like in a neighborhood. It's in the neighborhood of L is a solid torus, and this means the element correspond to Pn. But yeah. So roughly speaking, that's a curve that running around L n times, and we define the skein dilogarithm with this. It's just a formula, and it has some nice property which we'll introduce later. But then we can define the skein cluster mutation to be the adjoint action of this QL. So for any simple closed curve L on gamma, we define a cluster mutation. Okay, now this also notation called mutation of a graph. So we say that the mutation of the graph is just a local operator. We just like somehow twist this by 90 degrees, and that's a mutation. For each edge of gamma, we can do such a mutation. And the point is that any two graphs on S2, if they have same number of vertices, then we can mutate one to another. Yeah, just doing this kind of operation. So so let's do this trick on our lambda gamma. So do the recall that our lambda gamma. So our lambda gamma has a 2-to-1 branch cover to S2, and this is a 2-to-1 branch cover. And the branching point are exactly this the vertex of this gamma. So whenever I write an edge E, actually above E, it's a simple closed curve on lambda gamma. So for each edge E, we can define a quantum a skein dilogarithm living in this this algebra. And then for each edge E, we can define a custom mutation. So here now comes our main theorem. So this custom mutation will send send a gamma to a gamma prime. So this means that if we do such a mutation, then what happens to our equation? So our equation also change by a cluster a skein cluster mutation. So well, if we write this down, this means that QE A times QE inverse is A gamma prime. Sorry, this is gamma. So roughly speaking, that's the main theorem. So this recurrent relation is preserved under cluster mutation. And now, let's say what this imply if we know that oh wait, sorry, this another typo. So sorry, it's so much typo. So if we know that the solution to this equation is unique, and then let's look at the equation here. So this is our theorem, right? This part is our theorem, and we just replace this by definition is this thing. And then what does this imply? It implies that this is also zero. So QE inverse L gamma prime. This is also a solution of this equation. So we know this because the solution is unique. So this one is this one. So we have this. So the conclusion is that we have this formula. So this means that whenever we do this mutation, we mutate the graph, or if we mutate the graph at edge E, then the wave function would change by multiplying a quantum skein dilogarithm. Sorry for the time, but just very fast. So I'm LRA. Yeah. So I already to say the main theorem. So it's like this. So there's one more thing, because any two graphs can be mutated. Any two graphs can be mutated from one to the other. So roughly speaking, so all graphs are like mutation equivalent. So we only need to know like one the wave function of one graph, which is the following. We call this necklace graph, and the wave function, because we know the Lagrangian filling of this is exact. So the wave function of this necklace graph is 1. Yeah, and indeed you can also solve the skein equation of this wave function, and you can prove that 1 is the only unique solution. And now, so the conclusion is that if we have a graph, so we start from this necklace graph, and we do mutation. We mutate at the edges. And in the end, we get so we mutate the graph like E1, and we get a let's say gamma n minus 1, and then we mutate E2, and somehow we get our sorry, let's call this gamma 1, and in the end we got our gamma, and then we know that the wave function of this L gamma would be a product of this quantum skein dilogarithm. So any question for that? The point is this yeah, the theorem where we know how this equation changes when we mutate the graph, and then we know how the solution changes when
let me maybe I don't know, I have a question, but
sorry,
you don't have too much. I mean, I'm just curious. your skein algebra, at least probably for genus 1, should somehow relate it to the maybe to the elliptic hole algebra or
Yes,
something.
yes.
And so then you have this elliptic, and your skein algebra has a homomorphism to the quantum torus. Yeah, I mean, it's kind of resembles what I
Yeah,
can
it's this way. We have
it
this
resembles our old story with Maxim about this whole algebras with a homomorphism to quantum torus. And so then your wave functions look roughly like this dt series, which we defined at the time. And so then the product of quantum dialogues, it looks like, I don't know, like product over all arrays, this factorization of the dt series.
Yeah.
I
In the
don't know
torus,
whether
yeah.
it's just a resemblance or indeed it's
Yeah, exactly. So in the case of torus, everything matches up. Yeah. This main computation before, and they do match up. So here is the example. Yeah, I was going to talk about, yeah. So
okay.
So in the case of Aganagic-Vafa brane, and it would be the dilogarithm is this thing, and the result is that it's product with real quantum dilogarism. So that's the thing, and our computation matches up the topological vertex. And maybe I'll take 3 more minutes. So it's yeah. So sorry for taking too much time, but there's one last thing that I want to say, which is this quantum dilogarithm actually satisfy a pentagon relation. So if we have 2 curves, A and B, they are simple closed curve on sigma, and they only intersect once. And so we denote A plus B by their connected sum. So we do a surgery and yeah. So this is A plus B, and we have such a pentagon relation. So when we do this rank 1 reduction, we get we get the pentagon relation for the quantum dilogarithm, and this as Yang mentioned, there's this suggestion from punctual torus skein algebra punctual torus to elliptic algebra. So this pentagon relation reproves the pentagon relation in elliptical algebra, and because this thing acts on the ring of symmetric function. Yeah, maybe that's called like Fock space or something. So this reproves the example. This reproves the result by Garsia and Mellit. So yeah. That's I think that's all I say. Yeah, thank you.
Yeah, thank you very much. Are there any questions? Yeah, so let me ask. I mean, I asked already many questions, but let me ask you sort of a stupid questions, because you mentioned this Mellit and Garcia paper. I mean, technically, it's not related to affine Grassmannian, it's pure combinatorics. But somehow this, how to say, this elliptic hole, I mean, probably it's too long story to say it in a couple of words, but elliptic hole algebra, it can appear as a generalization, sort of a one-dimensional generalization of some zero-dimensional whole algebra, which is a whole algebra of the Jordan quiver, of the quiver with one vertex and one loop. and kind of nilpotent representation. So the whole algebra is a symmetric. Okay. This is sort of a zero-dimensional example in the sense that it's quiver, just quiver with one loop, and so from this you can go in two different directions. One is elliptic whole algebra, as in your talk, and as Schiffman and Vassero did, and then Schiffman and Bourban long ago. But there is another possibility. When you embed not elliptic, sorry, when you embed this whole algebra of the Jordan quiver to the affine Hecke algebra of the positive affine Grassmannian, basically under this map, the characteristic function of the orbit corresponding to some partition lambda goes to the characteristic function of the corresponding orbit in the affine Grassmannian. They just parameterized by the same thing. Okay, and then you can take the projective limit, and so you get that the whole elliptic, the whole algebra of the Jordan quiver, and you consider nilpotent representations, can be identified with an affine Hecke algebra of the positive Grassmannian, and symmetric functions appear just because of the geometric Satake correspondence. So then this story. So in particular, you can see in this toy model example, you can see like whole Littlewood polynomials and some other features of the symmetric. All right, but now when you go to the elliptic whole algebra, then you see more complicated, like, McDonald polynomials, this kind of thing. So my question is whether they appear not in your story, like McDonald or generalized McDonald polynomials.
Oh,
Because
they doesn't, yeah. So this the proof of this pentagon relation is pure topological. It's just like it's a purely like low dimension topology proof, but I recover some results about
I understand, but you give sort of a geometric proof, and but the thing is that deeply inside of this elliptic whole algebra, I mean, the structure is intrinsically related to the geometry of the affine Grassmannian. And these symmetric functions, like including McDonald polynomials, they do appear from this perspective. And so then I'm just wondering whether your topological story, especially since you mentioned local systems, maybe did you see any relation to the affine Grassmannian?
Sorry, I haven't thought about that, but yeah, that might be something interesting to explore. So
that's I said it's kind of a vague question.
But that's very interesting. And thanks for sharing the insight. Maybe I'll think about that. So
all right. More questions?
I have a quick question. Probably it's very elementary. In your slides 21, and you described the skein algebra for S1 cross D2.
21.
Yeah, page 21 slides.
It's 21. Here. This one.
No, there is a slide where you say the symmetric function algebra is exactly the skein algebra of S1. Yeah, for this solid
This one.
torus.
Oh, yeah.
Skein algebra actually is a symmetric. Yes, the bottom of this one. So can you just give at least our students some simple example that here we have a few symmetric functions.
Oh,
and
yeah, sure.
They are corresponding to what kind of knots. And also here, this S1, this solid torus is 3-dimensional, right?
Yeah. It's 3-dimensional, but it's annular. It's a second annulars, right? So when I write,
So earlier you described the skein algebra for surfaces.
Yes.
Mm.
So it's the same here. It's a skein algebra or skein module of annulars. It's the same as the skein module of solid torus because we glue. Remember, like we glue this edge to this edge, right? So when I draw this picture, it's an annulars, and a second annulars is solid torus. So when I draw such a diagram, the green bridge is indeed a link in the solid torus. Right.
Okay.
The green thing.
So in this case, the solid torus is really just a torus, not your earlier notation. You have I, your definition. You made it 4-dimensional, then making the boundary.
It's the same. So what I define.
Earlier you defined for the sigma. So the skein sigma means skein of sigma with I.
Yes, exactly.
Okay, so now let me go back. So there are a few elementary symmetric functions or some standard symmetric functions. Can you read off some of this?
Yeah, it's exactly here in this diagram. So recall that the Schur polynomial are this, right?
So this is in terms of Schur polynomials.
Yeah, in terms of
Schur functions.
Yeah, Schur functions. So whenever I have a partition here, we have a symmetric function, right? That's the Schur polynomial, and it looks like the first 3 terms. The first 2 terms looks like this, and this formula.
These are the easy power symmetric functions.
Yeah.
Those are very special.
Here, that's some example. So when you have a single box, it's this. When you have 2 boxes, it looks like this. So when you have like 2 vertical boxes, it looks like this. And remember,
whenever to elementary symmetric function, I believe, right?
Sorry, what?
2 vertical boxes.
Yeah, sure. Yeah. So it's this is like sigma xi xj where I is not j. Yeah. So
this is the elementary symmetric function.
Yeah. So that's so this isomorphic is not trivial. It's not obvious. It's a hard theorem. Like by Moulton and other people, but it's like 20 years ago. But it's a sequence of papers, but it's not easy. So and those are the first several terms, and you can say that this is not obvious, right? Yeah. They have a way to write down this correspondence. There is a formula, but it's
so with that, probably we'll continue with the question on Yan earlier asked it, because you said the local system earlier, but the GL1 local system.
Yeah.
And then you go to the GL infinite local system.
Yeah.
Here because you are using the Schur functions, all these Schur functions, given the partition, the Schur functions is a reducible character of some GL. When N is large enough, larger than.
Yeah.
So that's you take the limit. So do you see from whether the geometrical or topological way to see how the irreducible representation of the GLNs actually appear, or acting on this skein modules?
For that part,
you probably don't still see.
I probably don't really know this. Yeah, but that's sorry, I don't really know. But also, this is like what I write down. well, what I write down there, so this sentence is just the key words here is morally. There's no mathematical
understand.
rigors. Yeah, but you should understand it this way. Yeah, as you mentioned, in this way, it's because the local system on solid torus is same as local system on S1, so it's just a representation of GL infinity, and as you mentioned, it's somehow the same as like symmetric function, right? And also
the short functions gives you a reducible.
Yeah. So it's somehow the same
system.
And also if it's a torus, so in other words, if you glue this edge with this edge, then you get a torus, and the skein algebra of that torus is equivalent to the double alpha Hecke algebra, which somehow could be viewed as a quantization of local system on T2 on the torus.
I see.
Yeah.
Okay.
So for other surface, I think it's maybe there are some partial results. I don't know, like the scheme module. Some variation scheme module is the factorization homology of So something like that. But sorry, I don't know the details of that story. So
okay. Oh, that's good. Thank you very much.
Yeah. Thank you.
Okay. More questions? Well, if not, thank you very much, Mingyuan, for the nice talk. And there is a paper in the archive, so people can look.
Yeah. It's my pleasure. Yeah, thank you.
Yeah. Okay, thank you. And this is it for today.
Yeah, thank you.